Hello, we are Group 6. I'm Abby. This is Kyle and Jung Chang, and today we're going to be talking about our Project 3 for the course IE470. To give some background of the project and the project description, we were tasked with designing a system to backflush a swimming pool filter. So what that means is we need to produce 150,000 units of this valve with injection molding. We were tasked with developing two designs, the second one improving upon the first, both in geometry, process plan, in order to further minimize cost. The parameters around these designs, as I mentioned earlier, has to backflush as well as normal conditions. So you can see with this figure here, backflush means that it goes from the pool through the filter into the drain, whereas normal conditions is it goes from the pool through the filter the opposite direction and back through the pool. In addition to that, the hose connector is going to have an inner diameter of 1.5 inches, so we need to make our valve accordingly. And also we have to take into account the surface roughness of at least 180 microinches. So the overall objective of the project was to minimize the unit cost of the valve. So I'm Abby, as I said earlier. I'm the team leader and the design lead. Kyle was the process plan lead, and Jung Chang was the cost analysis lead. How we designed this project and how we managed ourselves was we really wanted to do an iterative process. So we were going to complete the design one completely, the whole thing, process plan, cost analysis, before we started design 2, so we could identify the appropriate improvements. That's apparent with our Gantt chart here on this page. I know it's pretty small, so you can't read it exactly, but basically how we designed it was that I would create the design, Kyle would go through the process plan, and Jung Chang would do the entire cost analysis before we would start design 2, so we could identify the proper areas of improvement and exactly how we wanted to change the design to yield the best results, which is how we really minimize cost. So to jump into our designs, we created two rotary design layouts, with the second design improving upon the first with new dimensions. So for both design 1 and design 2, we use the same raw materials for the housing and the spool molds. It's a 420 stainless steel rod, 4.5 inches in diameter, a foot in length, and we part that differently based off the designs and the molds depending on the size of the individual piece that we need. And then the second raw material that's very essential to the project is the injection material. So here you can see how we decided on our polyethylene choice was we graphed the cost versus the chilling time. The chilling time could be found with the max thickness of the design. So as you can see, our max thickness changes from design 1 and design 2, and I'll discuss that more later, but this was a crucial aspect in our designs, as we wanted to decrease that thickness so we could decrease chilling time. But why we chose polyethylene is because clearly you can see here that it's the least cost and the lowest chilling time, so it's the best choice for the injection material. Jumping into design 1, the design 1 housing is 2.9 inches in height, is 0.375 thick, and the portholes are 2 inches in diameter because, like I said earlier, the hose is 1.5 inches inner diameter, so we were assuming that the hose was 0.25 inches thick. The spool for design 1 is in a Y-shaped. It can be moved back and forth to allow for that normal and backflush conditions. The thickness of the bottom is 0.375, which is the same as the thickness of the housing. This is a very standard design for the rotary layout, so we thought it was a good design 1. So this is a quick video just to show how exactly design 1 works. So as you can see, the spool will be inserted into the housing. It moves back and forth to allow for normal flush and backflush conditions, making that rotary layout that was required. So the design 1 housing mold, how we are going to make this, we split our molds into two sides. So the top side is side A and the bottom side is side B. And how this works is side A comes down on top of side B in the molding sheets that were supplied, the 3x3 molding sheets. And the injection material, well, first 5 2-inch pins are inserted into the portholes using cam pins. And then the injection material, polyethylene, is inserted. And then once it's cooled, the cam pins release those 5 2-inch diameter pins. And then the mold comes up, and then injector pins on the bottom push the plastic out from the side B mold. So because of the scope of the project, the ejector pins and the cam pins and the runner are not modeled in these diagrams, but it was just assumed that that would be an effective way of molding. So as you can see, these are the dimensions, and the slash is where the plastic would fill in. So we designed the spool mold in a similar way. Side A comes down on top of side B. The injection material is inserted, and once it cools, the cam pins push that plastic up. Really quick to discuss, Kyle's going to go into it more in detail later, but really quick to discuss how we are going to machine this. He'll talk about it, but just as the visual is up on the board, for this side B mold, we're going to take the 2-inch diameter drill that we use for the portholes and initially clear out the cavity and then mill out the rest, which will save us a lot of machining time. Kyle again will discuss that later, but I just wanted to mention that here. So after design 1, we wanted to identify all the areas of improvement and how we can make design 2 better to minimize cost. So working closely with Kyle and Jung Chang and the other 2 parts of the project, we saw that the main factors affecting cost were the raw materials and the depreciation of the injection molding machine. So when Jung Chang finished his analysis of design 1, it was clear that the raw material, polyethylene, that cost was really high, so we wanted to decrease that cost. Which means that decreasing the thickness of how much plastic was needed was essential. And also decreasing the thickness we found was going to decrease the chilling time, which meant that the depreciation of the injection molding machine would also decrease, which Jung Chang found in his analysis. So we decided to change the spool shape because the Y was way too thick. That material, it was taking way too long to cool. But decreasing the thickness of our designs meant that we were going to have to machine more. So we worked with Kyle in the process plan to find the optimal thickness value. So we weren't machining too much more, because that would require more cost too, but to find the optimal thickness value. So we came up, and also in addition for design 2, we needed to add a locking mechanism so our spool would lock into the housing. So we did that with adding a veneer pen. So the veneer pen was going to be inserted into the wall of the housing. And so in order to do that, we needed to have rods that we could insert into our molds, and so when the material would flood in, it wouldn't flood into that small hole. So we are going to purchase these rods as well as the veneer pens and have 2 holes in the bottom of the spool lid and 1 hole in the housing. So to insert the pen, and then when the spool moves back and forth, it would click into those 2 holes in the lid of the housing. So for our design 2, as I said, we decreased thickness drastically. So the thickness is now 0.25 of the housing, of the wall of the housing. We kept their diameter holes at 2 inches. And also decrease the overall height of the housing, which means that we could part more materials from that initial long rod, again decreasing our raw materials costs, which Jung Chang found was really high in design 1. The design 2 spool, as I said, we changed it to a T shape, which decreased the thickness of that Y, which really decreased our overall chilling time of the material and also the cost of the raw material, polyethylene in general. So the Y is the same thickness of 0.25 as the housing wall, and it works the same way, or the T, it works the same way as the Y. It moves back and forth, allowing for both conditions. It's just a lot thinner, which means that we save a lot in cost. So this is a video of the valve 2 design. It's very similar to design 1. It's just a lot more, optimized in terms of thickness and moving back and forth. But as you can see, it allows for both functions. Normal flush and back flush. So the design 2 housing mold is very similar to design 1. We liked how we modeled that. We liked how we modeled the molds. Side A comes on top of side B. We decreased the thickness of the molds, again, to save money on raw materials. The main difference is we inserted those 0.125 diameter pins in the housing into side B, so they stuck up into the blank area where side A comes down, which would allow for a hole to be formed in the material. That they stick up 0.531 inches because that is the body length of the veneer pen that will be inserted later. This is a video that really shows how our mold works. So the orange is the material, but the side A comes on down to side B. The 5 2-inch diameter hole pins are inserted. Material goes in, and then that plastic once it cools, is pushed out with ejector pens, and that is the finished plastic mold. So for our spool mold, again, it's very same as design 1. Side A comes down side to side B, except it's in a T shape. Again, the main difference is our locking mechanism. We insert 2 small 1.125 diameter pins into the side A of the spool mold, and they stick out 0.035 inches because that's the maximum ball reach of the velour pin. So that means that there'll be 2 holes on the underside lid of the spool where, moving back and forth, that ball will insert when in the different conditions. This is a video of the spool mold showing how side A comes down on top of side B, the material will be injected, and then it will come up and the ejector pins will push out the finished plastic mold, or the finished plastic spool. So this depicts how our design works in terms of a functional flow. So the left is the normal flow and the right is the backflush. As you can see, it goes from the pool through the filter and then to the drain for backflush and back to the pool for normal flush. This is an overall summary of our dimensions. Again, the main change we made was the thickness. That was a drastic change that Jung Cheng found after his cost analysis that we needed to change in order to decrease the total volume in plastic per unit. We also decreased the overall height of both the spool and the housing, which saved money on raw materials as well. Like I just said, the overall volume and material removed decreased, which was a large cost saving, and it also decreased the amount of plastic needed, which really was beneficial, and we were happy with this change from design 1 to design 2. So now Kyle will discuss the process plan part of the project.
Yeah, as Abby had mentioned, I'm the process lead for this part of the project, and she also mentioned how an iterative process was used, so I was assisted heavily with Jung Cheng and Abby on both cost and design. Since this was our first initial run-through of the injection molding process, we knew that our molds were going to be a heavy consideration in our manufacturing process. And as well as that, the injection molding process would be assumed to be highly automatic once the molds were completed, just to assume for operator cost and labor. So our various shapes of molds, as Abby just showed you, require the following machining processes. We have to part the raw materials, we have to turn for making the outline of the molds, we have to drill the inner cavities and portholes on the molds, we have to drill the nodes, we have to drill the locking pin inserts, we have to mill the finishing cavities, as well as milling the Y and T-shaped spools. So for our tool selection for parting, we selected a bandsaw. We chose a bandsaw because of its long durability and relatively low material removal rate. For turning, we selected a stainless steel 420 C6 carbide insert with 8 edges, which also has a nose radius of 0.008 inches. For drilling the cavity and portholes, we selected a high-speed steel 2-inch drill bit. For drilling the knob cavity, we chose a high-speed steel 0.5-inch drill bit, and for drilling the locking pin insert holes, we also chose a high-speed steel, but this time was 0.125 in diameter. For milling, we only chose square end mills to mill the high-speed steel, and those were to mill the stainless steel, and those were made of either high-speed steel or solid carbide. So the housing mold side A for design 1 and 2, which was used to finish the major cavities, used a 1-inch in diameter high-speed steel square end mill with a tool life of 4 moles. For the spool mold for side B for design 1, we used a 0.625-inch in diameter high-speed steel square end mill with a tool life of 4 moles as well. And for the spool mold for side B for design 2, we used a 0.75-inch in diameter high-speed steel square end mill with a tool life of 4 moles as well. For the spool mold in side B, since the cavities are going to be very deep and cut, we assume the tool life to be 2 moles instead of 4 moles due to the heavy pressure on that process. So for the Y shape in design 1, we utilized a 0.375-inch diameter solid carbide square end mill, and for the T shape in design 2, we utilized a 0.25-inch diameter solid carbide square end mill. So for our machine parameters for parting, we had 2 assumptions. 1, we assumed that our bandsaw was going to last the entire process, and 2, we assumed that the parting process would last 1 minute for each cut. So for design 1, we needed 16 raw materials to part into 48 cuts for a parting time of 48 minutes. For design 2, we only needed 13 raw materials to part into 52 cuts for the molds. But adding the pin inserts in design 2, we had to use 2 raw materials to part into 46 cuts. Since the parting pin inserts only have a diameter of 0.125 inches, We tried to assume a parting time of less than 1 minute, say 5 seconds, to be more realistic. However, when going over to Zhengcheng for cost, we realized that parting really doesn't impact cost at all. So to keep the assumptions very consistent, we just kept the assumption of 1 minute for parting time. For turning, we used the indexible C6 insert that was shown previously, and that was going to follow the Taylor tool depth equation. We also applied a cost per inch of cut versus cutting speed, as you can see on the right here. And as you'll also see, the cost per inch of cut increases drastically with the cutting speed. So for our range of cutting speed between 300 and 700, we chose the minimum surface speed that was possible to optimize our cost. We also chose the maximum horsepower, which was collected from the machine data handbook that was given to us in the project in order to be applied to the spindle. So our final parameters for turning was 360 surface speed per minute in cutting speed, a 0.062 inch depth of cut, 10 horsepower, an MRR of 13.3 inches cubed per minute, an RPM of 305.6, and a feed rate of 0.05 inches per revolution. So for turning, the only parts that need to be turned in design 1 and 2 were the housing side B and the spool side A. So as you can see here, the length of cut per pass in design 1 for turning was 2.8 and 2.3 for the housing and spool. That decreased to 2.2 for both the housing and spool in design 2. With that decrease in length, the total passes decreased from 11 to 9 and 5, and that drastically decreased our turning time for both design 1 for design 2. And so our total turning time for design 1 was 50.56, and for design 2 was 29.28 minutes. So for drilling, we used drilling to make the holes and for removing the majority of material from the cavities, as mentioned before. All the drilling data that you see here was collected from the handbook that was given to us. Just to summarize, we used a 2-inch, 0.5 inch, and a 0.125 inch drill bit. The cutting speed was very consistent across the board at 65. The horsepower was again maximized at 1.5. The MRR was consistent at 2 inches cubed per minute, and the feed rates are 0.0052, 0.0205, and 0.0820 inch per revolution across the board. So for drilling, for design 1, housing side A, we needed a 2.9 inch drilling length requirement for the cavities and a 0.375 inch drilling length for the ports. For the spool side B, we needed a 2.6 inch drilling length for the cavity and a 0.1 inch length for the knob. In design 2, both the housing and spool only required a 2.4 inch drilling length for the cavity, and for the housing, we only needed a 0.25 for each of the 5 ports, and the knob depth decreased to 0.06. We also had to add a 0.05 inch length for the pins. And as you can see in our machining time for each mold, adding that 0.05 inch length really didn't add any time to our drilling time for our second design. So our total drilling time decreased from 185.08 minutes to 151.89 minutes from design 1 to design 2. So our final parameter was milling. We used milling to remove the materials that cannot be removed by drilling or turning. So as you can see here in this design on the right, we would drill out that 2 inch diameter hole and then use the 1 inch diameter mill to mill out to the proper depth of cut. So for our milling parameters for design 1, housing side A, our total line removed was 25.53 inches cubed. For spool side A, it was 4.02 inches cubed, and for spool side B, it was 10.29 inches cubed. For design 2, you can see that the housing side A decreased to 21.13 inches cubed. Spool side A decreased to 2.56 inches cubed, while spool side B actually increased to 21.13. As I had mentioned, that we knew that our design 2 was going to have increased machining time and milling due to our new spool. So what we thought about, me and Abby, was to maybe implement a new drill that was bigger in diameter to remove more material off the start. However, talking with Zhengcheng and cost, we realized that buying that extra drill bit would actually outweigh the extra 8 minutes needed for milling time. So to optimize our costs, we kept our added 8 minutes for milling time. So our injection molding layout is as follows. It has a 3 feet by 3 feet inch working space as defined by the project parameters. The diameter of the molds is 4.5 inches. We believe this is our optimal mold runner layout and mold cavity layout. All the molds are equidistant from the sprue, which is necessary for consistent flow volume and a consistent hydraulic pressure. So for our injection molding unit time, we assume that our cooling time is half of our cycle time. We calculated cooling time using the calculator that was given to us online in the Project 3 parameters. So as you can see here, in design 1, our cooling time was calculated to be 1.548 minutes for the housing and 2.752 for the spool. In design 2, that decreased to 0.688 minutes for both housing and spool. If you double both those numbers, you get the cycle time, and you multiply it by 150,000, you get the injection time for the entire lot size. So for design 1, our total injection time was 80,625 minutes. and for design 2 it was 25,800 minutes, which is a 68% decrease in total injection time, which is a huge factor in our cost, which Jung Chang will explain right now.
Alright, so again, my name is Jun Chen, and I'm with the cost analysis part leader. The rest of the group also contributed to the cost analysis part with their experience and skills. So, to approach cost analysis, the first thing to look at is the total process time. There are 4 parts of the total process time: setup time, machining time, workpiece change time, and the tool change time. The setup time was assumed to be 10 minutes for all the machines used in the manufacturing modes, including bensol, drilling press, CNC lathe, and CNC milling machine. The setup time period is counted once for each of the processes. The machining time is already discussed in the process plan. It can be directly used in finding the total manufacturing time. Workpiece change time is 2 minutes and counted each time for mounting new workpiece on the bensol, CNC lathe, press, drilling press, and the CNC milling machine. Tool change time is considered each time when the tool life is consumed. Tool life is only considered for turning and milling. According to their different applications, their tool lives are different. So the total time for the mold manufacturing process is shown here. For both design 1 and design 2, from this chart we can tell that comparing to design 1, the mold machining time actually increased slightly. However, the increase of mold manufacturing time is a fair trade for the decrease of total cost. Since the design 2's injection molding thickness is way less than that in the design 1, the cooling time, also the injection molding time, is greatly reduced, as the chart in the process plan indicated. Since all of the 16 molds can be fitted in a single working area, the only mold change time applied when switching the housing molds with the spool molds, which is an extra 40 minutes for each of the design. So in a similar way to the total time, the function of the total cost can be simplified to this. While engineering cost is a fixed cost and the overhead cost is 18% of the rest of the cost, the raw material and tool costs are probably referred to the information from the designated website and put into algorithms. Depreciation costs and operator costs are broken down into dollars per minute according to the assumption of 2,000 working hours per year. Later, they are counted into the cost of their corresponding machines. In this project, all the machines used to have a corresponding depreciation cost and the same operator cost except the injection molding machine. In the conversation with Mark, the MGL lab manager, we are provided with information that in common manufacturing scenarios, an auto injection molding machine is applied so that no operator will be needed for the injection molding cycle process. Accordingly, in this project, the operator cost is only applied on injection molding for the constant 40 minutes mold change over time for each design. So, the following charts and diagrams shows the categorized total cost of both designs. For the results, we can tell that the mold manufacturing process cost is only a small portion of the total cost. And any non-major reversion of the mold manufacturing decisions has ignorable impacts of the final cost. The major concern is the machining depreciation cost and raw material cost brought by the injection molding. Right after we finished the design 1, we applied the complete total cost analysis algorithm onto the manufacturing parameters. We observed that the cooling time is the most influential factor regarding the total cost. In consider of the cooling time is directly determined by the maximum wall thickness for the injected parts. We decided to reduce housing wall thickness and replace the Y-shaped stem with the T-shaped stem to shorten the cooling time. By doing so, both depreciation costs and the raw material costs are greatly reduced, since the total volume of the injection and the cooling time are decreased significantly. Even though the mold manufacturing time increased, the total cost is reduced by a great amount. So, for a better review of the cost saving, the unit cost of design 1 is 93 cents, while that of the design 2 is only 15 cents. This is a reduction of 46.2% within the designs of our group. The result has been checked multiple times through the whole project and is mathematically correct. The reasons for the low cost are, first, we assumed automatic injection molding cycle is applied, so the operator cost for the most time-consuming process is saved. Secondly, the project is based on some idealized and non-practical assumptions due to the lack of real-life experience about the actual injection molding industries. The unit cost is a theoretical minimized cost for our design too. However, from this project, the most important conclusion we made is that for a massive production scenario, like in this case, the most expensive process will be the actual value-adding processes in common industry. By saving cost of each unit's value-adding process, even at the risk of increasing the non-value-adding process cost, the overall cost will be reduced significantly. Thank you.